The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so review session on the first part of the Fourier chapter. These two topics that we've done and that homework is now coming on Fourier series, the classical facts, plus paying attention to the rate of decay of the Fourier coefficients is an aspect not always mentioned, and the energy equality is important. So it's not just, here's the function, find the coefficients. That's not all, that's part of it, but not all of it. And then the discrete series we're doing today. Okay, so those are the two topics for today, and then the next review session, which would be 2 weeks from now, would focus especially on convolution and Fourier integrals. Yeah. Okay, so I'm open to questions on the homework or off the homework. Always fine. I didn't know how many questions to ask you on the homework. I wanted you to have enough practice doing this stuff, because the time for this Fourier part of the course is a little shorter. Thanksgiving comes into it, so needed to do some exercise. And you've got a good question. Thanks.
I have a question on 4.1.18 on the homework.
Number 18 on the homework. Okay.
It combines the delta function.
Oh, yes. Okay. Right. All right. So that's the idea of that problem is I'm really asking you to read the two pages, the last two pages of the section that use Fourier series to solve the heat equation. So we've used, briefly, Fourier series to solve Laplace's equation. So that was just to recall. So Fourier series to solve Laplace's equation was when the region was a circle, the function was given, the boundary values were given, it's 2 pi periodic because it is a circle, and we solved Laplace inside. Because on the boundary, the perfect thing we needed was the Fourier series to match the boundary. Now I'm taking another classical application to the heat equation. So I made it the heat equation. So here's, this direction is time, this direction is space. The heat equation is ut equal uxx. If the coefficient, everybody here knows there would be a c in there, but let's take it to be 1. Then what are the solutions, and how does a Fourier series help you to match the initial function? So I'm given u of x and 0 here. Okay. This is at time 0. So that says at a time 0. So I have a bar. I have a conducting bar. And this is like, it's such a classical example that I didn't feel you could miss it completely, even though we look beyond formulas. But here's one where the formula shows us something important. Okay, so what are solutions to this equation? You look for solutions. So the classical idea of separate variables. Look for solutions that are of the form some function of t, maybe I'll try to use the same letters as the text, some function of t times some function of x. Okay, and the text uses, look for solutions, u of x and t that are of this form, some function of t, darn, I didn't remember it. Well, yeah, it's a of x, b of t. Okay, that's what I mean by separating. So those will be specially simple solutions. And when we go to match the initial condition, I'll just plug in t equals 0, and I'll see the a of x's. Well, what are they? In this case, so they're eigenfunction. Oh, I have to tell you about the remaining boundary conditions, don't I? Because that will decide what the a of x has to satisfy, and will decide what those eigenfunctions are. So let's see. In this problem, I think I picked free conditions. So I made the interval minus pi to pi. That's a change. Minus pi to pi, just so we'd have nice Fourier series. And here I have this boundary is free, u du dx, u prime, at x equal minus pi for all time. So up this line is 0. And also u prime at plus pi and all time is 0. So up those lines, heat's going out. That's what that means. Is that what that means? Or does that mean heat can't go out? No, heat is, yeah, no. So what's happening? Heat's not going out. Is that right? The slope is 0. Right, the slope is the temperature gradient. We're requiring the temperature gradient. So the ends of the bar are insulated. So this is insulated. No passage through, right? Is that what that means? Yeah. It's like there's nobody, it's cut off there. There's nobody, the rod isn't extended for heat to go further. Okay, so that tells us what the x and the t, what the a of x and b of t are. So here's the point. You plug that hoped for solution into the equation, right? So so I plug it in here. And what do I have on the left side? Just the time derivative. So that's a times a of x b prime of t. You see, taking the time derivative doesn't touch a of x. On the right-hand side, I don't touch b of t, but I have the second derivative of the x part. So far, so good. Now, a little trick. If I divide both sides by a and by b, I get b prime over b equaling a double prime over a. Right? Just put the a under here, put the b under here. Now what? This is like neat because that function is only depending on time. This function depends only on x. So both sides have to be constant. One it can't actually change with time because this side is not changing with time. And this couldn't actually change with x because that's not changing with x. So those are both constants. So both constants. Let's see, I'll maybe just put a constant. And various constants are possible. Okay, so now you see the point here. Now I have two separate equations. I have an equation for the b part, db dt, b prime. If I bring the b up there, I have equals the constant times b. And I know the solution to that. B of t is, as everybody knows, what's the solution to a first order constant coefficient equation? Just e to the ct b of 0. Good. We've got b. We've got a b of t that works. And now what's the a that also works? That has a double prime. And I bring the a up. So now I have a double prime equals ca. So the a that goes with it is, okay, I've used a c there. So what's the good, I want two derivatives should bring down a c. Let me change c to lambda minus lambda squared. How about if I look ahead, change this constant to minus lambda squared, because I want something where two derivatives bring down minus lambda squared, and what will do that? Any amount of cosine lambda x, right? Because two derivatives will bring down a minus lambda squared, and any amount of sine lambda x. And this is now e to the minus lambda squared t. I'm doing this fast, but actually it's totally simple. The conclusion is that I now have a bunch of solutions of this special separated form where b of t could be that, and a of x could be either of those or any combination of those. And I have to use the same lambda for each so that the two equations will work in the original problem. Good. Now, so far, no boundary conditions. What I've got so far is just a lot of solutions. These times that, with any lambda. But of course, the boundary conditions will tell me the lambdas, first of all. And how do they tell me? The only boundary condition I have is this free stuff. So it's free. The slope should be 0 at pi and 0 at... So that's the x direction. So that's going to tell me, I've forgotten, do I want cosines or sines? Cosines. I want the derivative to be 0 at pi. Yep. So I think I want cosines. Good. And then lambdas can't be anything at all because should lambda be an integer or something like that? I think maybe lambda should be an integer because I want to plug in pi. So let me take the second derivative. Is minus lambda squared cosine lambda x. And then I want to plug in lambda equal x equal pi. And I want this to be 0. So lambda should be an integer, is that right? At multiples of pi, the cosine is 0. Yes. Is it? No. Did I want sines? Maybe I wanted sines.
We want the first derivative to be 0.
Oh, it's the first derivative I'm looking at. Ah, thank you. Thank you. Okay, good. Yep, thanks. Okay, now I've got it. Thank you. And now I see lambda should be an integer. Lambda should be 0 is, yeah, 0 is all right. That's a constant term. Yeah, we need that. 0, 1, 2, and so on. So do you see that I've now got let me write now this. Now I can take, I've got a lot of solutions, and I have a linear problem, so I can take any combination. So finally I have, final solution is that u of x and t is any combination with coefficients I'm free to choose of a of x, which is cosine of nx, because lambda had to be an n, and n could be anywhere from 0 on up, times e to the minus lambda is n, so that's n squared t. Did I get that? Let me put it on a circle and step back. What's up? I could have negative n's. Would they give me? They wouldn't give me anything new, right? I mean, cosine of nx and cosine of minus nx are just one's just the negative of the other. Yeah, yeah. So these are the good guys. I've got a cosine series because I've got free n's, right? Because of the boundary conditions. Do you see that? That's pretty nice. There's my a of x. There's my b of t. I can take any combination. Usual stuff. You get to that solution. Okay, and now I have to meet the initial conditions, right? Boundary conditions are now built in because I chose cosines, or you did. Now this will tell me what the c's are. I'm going to set t equals 0. At t equals 0, I'm given the initial condition, u of x and 0, and I have this same sum of cn cos nx e to the 0. So this will tell me the c's are the cosine coefficients of the given initial condition. So I expand, so here's where Fourier series is paid off. expand the initial function in a cosine series, and then go forward in time. This is just the old e to the lambda t. Only the lambda we're talking about here is minus n squared. And it's you see what's happening here? What's going to happen for large time? So this is a very physical problem that I think you cannot take 18085 without seeing this problem. You can't learn about Fourier series without using it for the initial value and then propagating in time with the usual exponentials for each one. And now as n increases, what do I see? Faster and faster decay. For large n, these are going to zero extremely fast. So that what you see with a solid bar, which starts with the temperature U in some probably not negative unless it's a really cold bar. But anyway, it starts with some initial temperature. That flattens out fast. The heat flows to equilibrate. What I approach is the constant term, C0. This approaches C0 because all these other n positives, that they go to 0. So the heat distributes itself equally. Okay, and now I guess the particular u of 0 in the problem was a delta. Okay, and the heat, so the particular u of 0 was from that really hot point. So we know the coefficients. We know the cosine coefficients for the delta function. We know these c's, and what were they? 1 over 2 pi was c naught, and the other c's were 1 over pi, I think. Is that right? Maybe they're all 1 over 2 pi. Maybe, yeah. Whatever. They disappear fast, and this is what we approach. So the heat from the delta function is, yeah. So is that everything the problem wanted? Yeah. I think we've done it. We'll put in the CNs to complete that picture into here, and then C naught is the one that survives over time. Yeah. So that's I guess once I got rolling, I couldn't stop, and that's you. For investing time this afternoon, you get a fast look at this classical problem of separating the variables, using the Fourier series for the initial function, and recognizing that we're doing this on a finite interval. If the bar was infinitely long, then we would be talking about Fourier integrals, and that's what's coming up a bit later. We would integrate instead of sum, yeah. But the idea would not be different. We would have, if we had infinite bar, then we would not be restricted to n equals 0, 1, 2, 3. Any n, any cosine wouldn't have to be an integer at all. Any number, any frequency would be allowed, and so we would have to integrate then. Yeah. And that's a classical problem too. Again, it's come up in a modern way that the famous Black-Scholes equation, shall I just, so the heat equation is for 18086. Here we brought it up because we could solve it fast. But the actual, yeah, the most important solution I could give you to the heat equation would be the one that starts from that point source of heat, but on the whole line. The one that would be integrals instead of sums. Yeah. So we came pretty close to solving the most important heat equation problem, but we're doing the periodic case with just cosines, and the infinite line case would be the most famous of all. Yeah, and it has a beautiful form. And I was going to say that so the heat equation is pretty classical, but let's see, where can I write the magic words? Black skulls. Yeah, next to the heat equation. So that's the heat equation, but it's also, do you know these names, Black and skulls? Anybody in mathematics of finance? So these much despised derivative options. So people on Wall Street, traders, will carry around a little calculator that solves the Black-Scholes equation, so they can price the options that they're bidding to buy and sell, so they can price them fast. And that little calculator does finite differences or a Fourier series solution to this Black-Scholes equation, which actually, if we change variables on it, is the heat equation. So that what you see here is actually important on Wall Street, except it's probably not the right moment to mention it, right? Because these, so you could blame the whole meltdown on mathematicians, but that wouldn't be entirely fair. They didn't mean it anyway, but that's been the biggest source of employment, I guess, apart from teaching, in the last 10 years. People who could work out the partial differential equations, and they get more complicated than the heat equation, you can be sure. For what an option, so the classical one, these guys are economists at MIT and Harvard, or they were, and I guess maybe the Nobel Prize in economics came to part of that group, and also to Merton. Maybe possibly Black died before the time of the Nobel Prize. Anyway, they were the first, and it's a beautiful paper to figure out how do you price what's the value of an option to buy that allows you to buy or sell a stock at a later time. Yeah, so well, of course, you have to make assumptions on what's going to happen over that time, and that's where Wall Street came to grief, I guess. You could, if you had to put it in a nutshell. I mean, the options, the standard, straightforward options, those are fine using Black-Scholes, and then what's happened is they now price more and more complicated things, to the point that the banks were buying and selling credit default swaps, insurance swaps, that practically nobody understood what they were. It's just assumed that if there was always a market for them, like insurance, somehow it wouldn't happen and you'd get on. But it happened. So now we're in trouble. Okay, that's not 18085, fortunately, or math. But anyway, a lot of people got involved with things they didn't really know about, and then were selling them, as well as, of course, the mortgage problems. Anyway, I don't stop with that one. Okay, ready for other questions on our homework or these topics? Yeah. Okay.
Way off, but
okay.
when I think of a Fourier series, I imagine little waves being built up and then they
okay.
code of shape, whatever we're trying to
Right.
talk about.
Yeah.
But with the discrete, I guess I don't have an image in my head.
Have an image of waves.
What
Oh,
we're doing, I just,
yeah.
is there a way you could?
I suppose if I had to have a picture of the discrete thing, if my picture of the function case was a bunch of sines and cosines somehow adding up to my function, And if I'm solving the heat equation, then those separate waves are maybe decaying in time here, so that when I add them up at a later time, I get something different. Or if it was the wave equation, which is probably your image, they're moving in time, so they add up to different things at different times because they can move at different speeds. Yeah, so a function is a sum of waves, right? Then what would the discrete guy be? I guess I would just have to imagine the function as only having those n values, and my wave would just be, you know, a wave might be just n values there. But still, as if I have a time-dependent problem, maybe that thing is pulsing up and down. It's just that it's only got a fixed number of points, and I'm not looking at the whole wave on a, yeah, but I don't think it's essentially different. And of course, the fast Fourier transform and the discrete case is used to approximate the continuous one. Yeah. Yeah, you could look in numerical recipes for a discussion of approximating Fourier series by discrete Fourier series. I mean, that's an important question because, of course, Fourier series has got all these integrals. The coefficients have come from an integral formula, and we're not going to do those integrals exactly, so we have to do them some approximate way, and one way would be to use equally spaced points and do the DFT. Yeah. Can you just remind me what that integral formula is? I don't want you to, it was on the board today. What's the formula for the coefficient CK in the Fourier series? I'm really just asking you this because I think you should have it in some memory cache, in fast memory rather than in the textbook. Okay, so what's the formula for CK in the Fourier series case? Everybody think about it. It's going to be an integral, right? And I'll take it over 0 to 2 pi, I don't mind, or minus pi. And what do I integrate? This is the Fourier coefficients of the function f of x. So I take f of x. I remember to divide by 2 pi. I'm doing the continuous one. What do I multiply by to get the coefficient? E to the minus ikx. So I've forgotten whether I assigned some of these very early questions that just gave you the function and said, what's the coefficient? If I just look at 1 or 2, suppose my function is f of x equal x. I guess in that problem, in problem 1, I made it minus pi to pi. Suppose f of x equals x. So you have to integrate x times e to the minus ikx. Well, you got an integral to do. Okay, it's doable, but not instantly doable. Let me ask you some questions and you tell me about it. So draw the function. The function is x from minus pi to pi. And tell me about the coefficients. How quickly do they decay? How quickly this is like some constant over k to some power p, and what's p? What rate of decay are you expecting for the coefficients? Well, you say to yourself, it looks like a pretty nice function, smooth as can be, but what's the answer here? The rate of decay will be, what will that power be? 1. Because the function jumps. The function has a jump there, and the Fourier coefficients have got to deal with it. So the Fourier series for this is going to be, if I took 100 terms, it would be really close, and then it'll go down here to the, but it's got to get there, and got to start and pick up below there. So it's got the same issue that the Gibbs phenomenon that the square wave had. It's got that jump. So it'll be it'll go like 1 over k. Okay, coming back, could you actually find those numbers? And how do you remember how to do integral like that? Well, look it up, I guess, is the best answer. But whoever did it the first time, well, it's integration by parts somehow. The derivative of this makes it real simple, and this we can integrate really easily, right? So we integrate that, take the derivative of that, we get a boundary term, and I don't exactly remember the formula, but it will be not, it'll have a couple of terms, but not bad, and we'll see this 1 over k. Okay, and that's the formula, right? If I changed x to something else, let's see, what can I just, as long as I'm looking at number 1, what if I took e to the x? Oh, easy, right? E to the x, yeah, let's do e to the x, because that's an easy one. Now e to the x looks like, so what's my graph of e to the x? It's quite small here at minus pi and pretty large at e to the pi. What's the rate of decay of the Fourier coefficients for that guy? Same. Got to jump again. Drops down here. So it'll be, so let's find it. Well, let's find those, do that integral. That's e to the x minus ik. Sorry. Let's put down what I'm integrating here. I'm integrating e to the x times 1 minus ik. Right? That's what I've got to integrate. The integral is the same thing divided by 1 minus ik. I plug in the endpoints minus pi and pi, and I've got the answer. And I divide by 2 pi. Yeah, so that's a totally doable one. Let's plug it in. 1 over 2 pi. And in the denominator is this 1 minus ik. Oh, yeah, well, there you see it already, right? You see already the 1 over k in the denominator. That's giving us the slow decay rate. And now I'm plugging in x equal e to the pi times 1 minus ik minus e to the minus pi 1 minus ik. So as k gets big, this is slow decay. Now what's happening here as k gets large? Oh, k is multiplied by I there. So this e to the pi ik is just sitting, it may even be just 1 or something, or minus 1 or whatever, is it? Yeah, k is just an integer. This is k pi I, that's just minus 1 to something. So all this is, all that numerator is minus 1 to the kth power or something times e to the pi. So e to the pi is there. E to the minus ik at e to the minus I pi k is just minus 1. And this is maybe e to the minus pi times the same e to the plus I pi k. I think that's minus 1 to the k. Well, wait a minute. Maybe they're not both. Whatever. It's a number. It's a number that's just of the size, of this size. There's the big number. There's the small one. And divided by that, that's the thing that shows us, yes, there is this jump. Right. Okay, that's a couple of sets of Fourier coefficients. You could ask yourself, because on the quiz there will probably be one, and I'll try to pick a function that's interesting and I mean, I don't plan to pick xe to the x or anything. Yeah. Okay, good. Yes, thanks.
What is the idea of energy in a Fourier series? Like if one Fourier series has twice the energy as another, what does that mean?
Oh, I don't know. I guess, maybe we're talking about power and things like if we were dealing with electronics, I guess I would interpret that energy in terms of power. So that's what I'd be seeing. Yeah, I'm not thinking of a really good answer to say, well, why is that energy equality? But it's really useful. You know, so much of signal processing, and we'll do a bit of signal processing, is simply based on that energy or equality there and moving into frequency space and convolution. Actually, that's they would call it filtering. So we'll call it filtering when we use convolution, but it's pure convolution. It's pure linear algebra for these special bases. Yeah, so okay, I could try to come up with a better answer than, or more focused answer than just to say power or point to use an an electric power word is just one step. Yeah, thanks. Yeah. Yes. 4.3, 8, and 9. Let's just have a look and see what they're about.
Taking mass Fourier transforms and given.
Okay, just some regular guys. Yeah, so that.
Those two vectors are orthogonal to begin with, and then.
Okay, let me look at. Do you want me to do 4, 3, 8?
My question is.
Yeah.
The results of that show that the vectors in k-space are orthogonal, and the ones were orthogonal in x-space. Is that always true, or is it just?
Yes, good question. Okay, so 4, 3, 8 gave a couple of vectors a little bit like the ones I did this morning. I mean, here the C in 4, 3, 8 has a couple of 1s, and this morning I just had a 1, 0, 0, 0, but no big deal. Now, yeah, so why is it, so if two vectors are orthogonal, are their transforms orthogonal? I think yes. Yes. The Fourier, so so maybe this is worth a moment here. Yeah. Because what do we, let me write down the letters for my question and then answer the question. Okay. So suppose I have two vectors, C and D, and they're orthogonal. And then I want to ask about their, if I multiply by the Fourier matrices, are those orthogonal? That's sort of the question. So here are the vectors in frequency space. Here they are in physical space. I don't mind if you started in physical space and went to frequency with F inverse. Same question. Does the Fourier matrix preserve angles? Does it preserve angles? Do these matrices, and F wouldn't be the only one with this property, do they preserve length, right? If you preserve length, do you preserve angles too? Preserve length, you're just looking at one vector. Here we're looking, we know that we preserve length, and how do we know that? Let's just remember that. So here's the length question, and this will be the angle question. So this is the energy inequality. Coming back to that key thing, this is C bar transpose C. And over here we have FC, FC. And this is what I did this morning. So that's C bar transpose F bar transpose FC, right? That's why the bar as well as the transpose, because we're doing complex. Okay, let me make a little more space. And what did we do this morning? We replaced that by, well, I wish it were the identity, but it's n times, it's a multiple of the identity, that's what matters. So this was n, this is the identity with an n, C bar transpose C. So the answer, the conclusion was that this thing is just n times this thing. Well, n times this length. I'm expecting, oh, but over here we got a 0, so my n is going to wash out. Okay, let's just do the same thing for angle. This is the key energy inequality, equality for length. And all I want to say is this Fourier matrix, like other orthogonal matrices, is just rotating the space. It's sort of amazing to think you have one space, physical space, and you rotate it. I'll use that word because somehow that's what an orthogonal matrix does. Well, it's complex n-dimensional space. Sorry. So it's not so easy to visualize rotations in Cn. But it's a rotation. Angles don't change. And let's just see why. The inner product of this with this is C bar transpose F bar transpose, because I have to transpose that, times FD. What do I do now? This one was C bar transpose D with 0. You see you have it? There's, again, this fact that this rotation and inverse and the transpose is the identity apart from an n. So again, inner products are multiplied by n. Not only the length squared, which is inner product with itself, but all inner products are just multiplied by n. So if they start 0, they end up 0. Yeah. That was your question, right? Yeah, right. So if I have a couple of vectors, as I guess that problem proposed, it happened to propose 2 inputs that happen to be orthogonal, then you should be able to see that the transforms are too. Yeah, yeah. Can I ask you about question 2? Was that on the homework? Problem 2 in section 4.3? Was it? All I want to say is that's a simple fact that, let me just write that fact down so we're looking at that fact. If I look at this F matrix, it's so simple, but it leads to lots of good, it's just a key fact. That if I look at my F matrix, am I looking at rows here? Yeah, I happen to look at rows. Columns would be the same. It's symmetric. So here is row 1. Here is row 2. I'm sorry, that's row 0. This is row 1. And let me look at row n minus 1. This is w to the n minus 1. This was w squared. This is w to the 2n minus 1, and so on. Everybody's got the idea of the, and then all these in between rows, 2, 3, etc. And the question asks, show that this and this are complex conjugates. That row and that row are the same except conjugates. So if we look at the row number 1 in F, we'll be looking at row number n minus 1 in F bar. Now, why is that row the conjugate of that row? Why is this the conjugate of this? Why are those two conjugates? So I'm asking you to explain to me why W bar is the conjugate of W of this is this. So it's just one more neat fact about these important, crucial numbers W. And so how do I see this? Well, That's this is w to this is one way to do it. This is w to the n times w to the minus 1. And what's w to the nth? 1. Everybody knows w to the nth is 1. So I have w, I'm trying to show that, well, that we know that this is true. That, yeah, so we know that the conjugate of w, right? There's w. Here's its conjugate, and it's also the inverse. This w is some e to the I theta. This is some e to the I some angle. Then always it's sitting on the unit circle. So its reciprocal is also on the unit circle. It's the reciprocal. It has e to the minus I theta. So it's just the conjugate. That's the great fact. That's the beautiful fact about this, all these w's and their powers. Conjugate and inverse the same. Yeah, right. So that was the key to problem 2. I don't think I asked you to go through all the steps of problem 3, but just in case you didn't read problem 3, let me tell you in one tiny space what happens. In problem 3, you discover that the fourth power of f is the identity, except there's an n squared, because from 2 f's we got an n, so from 4 f's. So that's another fantastic fact about the Fourier matrix. That is, fourth power, it must be somehow, the Fourier matrix is rotating, somehow, I don't know, how do you understand that the Fourier matrix is, its fourth power brings you back to the identity, apart from, we just didn't normalize it so that we wouldn't, to avoid that n squared, so we have to use it. Yeah, that's pretty amazing. Pretty amazing. So if I had normalized it right, I could, if I took f over the square root of n, that's the exact normalization to give me to put the n's where they belong, you could say. Then the fourth power of that matrix is the identity. Yeah, but new math and new applications keep coming for these things. Yeah, I'll tell you actually. You could tell me the eigenvalues of this matrix. Yeah, this is a good question. What are the eigenvalues of a matrix whose fourth power is the identity? Yeah? 1. What else could the eigenvalue be? If the fourth power of the matrix is I, what are the possible eigenvalues? So this matrix is, can I call it M for the, or maybe U for the matrix F? So if U to the fourth is the identity, what are the eigenvalues? What could, well, of course, U could be the identity, but it's not. It's Fourier matrix. So what other numbers than 1 could be? So the eigenvalues could be 1. What else could they be? Minus 1 is possible, because minus the identity, that'd be fine. I and minus I. 4 possible eigenvalues. And when the matrix reaches, I think if you put the 4 by 4 Fourier, I don't know. If you put put the 4 by 4 Fourier matrix into MATLAB and see what you get for eigenvalues. I don't know if you get 1. I've forgotten whether you get 1 of each of these, or whether somebody's repeated at the level 4, but then go up to 5 or 6. You'll see these guys start showing up, different multiplicity, right? If the 1024 matrix has got these guys some number of times adding up to 1024, right? Yeah. So it's quite neat. Now, here's a question which I actually just learned a good answer to. What are the eigenvectors? what are the eigenvectors? You could give a sort of half-baked description because once you know the eigenvalues, but to really get a handle on the eigenvectors has been a problem that was studied in IEEE transactions papers, but not really not a nice specific description of the eigenvectors. And somebody was in my office this fall, a guy, a postdoc at Berkeley, who's seen the right way to look at that problem and describe the eigenvectors of the Fourier matrix. So that's like amazing to me that such a fundamental question was waiting and turned out to involve quite important, deep ideas. Yeah, okay. Okay, ready for one more for today? Anything? Any or not? Okay, so I hope you're getting the good stuff now on the Fourier series, Fourier discrete transform. Please come on Friday, because Friday will be the big day for convolution, and that's essential. That's the essential thing that we still have to do. Okay, see you Friday.